Hello, everyone. Today we have the pleasure of having Dr. Arthur Lalonde. Arthur Lalonde is an assistant professor of physics at the Université de Montréal and a principal scientist at the SHUM Research Center. He earned his PhD in physics from the Université de Montréal in 2019 and completed the Harvard Medical Physics Residency Program in 2022. Dr. Lalonde specializes in proton therapy, adaptive radiotherapy, and more recently, flash radiotherapy, with a focus on beam monitoring and dose tracking for ultra-high dose rate electron beam. So take it away.
Thank you very much, Julia. I'm happy to be here. Thank you for having me. So the title of my talk is High Speed, High Accuracy, Novel Approaches to Monitor Dose and Dose Rate in Flash Electron Radiotherapy. My presentation will look like this. That's the outline of my talk. So I'll do a brief introduction on flash radiotherapy and then discuss three topics on which my group and I have been working on the last year and a half or so. Let's jump right in. So as most of you are probably aware, ultra high dose rate or flash radiotherapy shows great potential to enhance the therapeutic window of radiation oncology by providing equivalent tumor coverage while sparing healthy tissues. The exact mechanism is not yet known, but it's been reproduced and observed in several animal models, as shown here on the picture on the right. That's from a review paper published earlier this year. So it's been reproduced over and over. And if I just highlight the modality, so here are the studies based on electron beams. So the large majority of the study of the flash effect was done using electron beams, mostly because that's the easiest modality to achieve the ultra-high dose rate condition. So we loosely define flash as a mean dose rate, an average dose rate above 40 gray per second. And that's much easier to achieve with electrons than any other modality, at least in a cost-efficient manner. So currently, electron beams really represent the reference modality to transfer the flash radiotherapy in a preclinical and clinical setting. There are still, however, several challenges that have to be addressed to enable the translation of flash RT into the clinic, but also to make reproducible and robust preclinical experiments. So if we want to compare flash versus conventional, we should ideally have the same criteria of accuracy for our flash grade that we currently have for our conventional grade. And to achieve that, we need to be able to achieve accurate dose calculation and treatment planning in an arbitrary geometry like a small animal or human. We need to be able to monitor the beam reliably in real time. And if the flash effect depends on dose rate, we also need to be able to monitor the dose rate in real time. And there's also a current absence of absolute dosimetric protocol for flash radiotherapy. So my group and I have been working on all these three topics over, like I said, a year and a half. So I'll discuss some of the work we've done on trying to address at least partially some of these issues. So the first part of my talk will be on Monte Carlo beam modeling. So for electrons, we know that the reference approach for dose calculation is Monte Carlo. That's what we do clinically. So that's probably what we should do in a experimental setup like flash radiotherapy. And one key element for dose calculation in Monte Carlo is to have a good model of your beam. So typically we'll model the linac head and the beam modifying components like jaws and scattering filters using informations provided by the vendor. And then the source parameters, the spot size, the distribution, and the energy spectrum will typically be optimized using measurements. We'll try to reproduce measurements by fine-tuning these parameters. Of all the source parameters, the energy spectrum is known to be the most crucial. And it can be challenging for compact linacs, which is most of the flash linacs are compact linacs not equipped with a bending magnet. So when you have a linac with a bending magnet, you can most of the time approximate the energy spectrum with a Gaussian function. For a compact linac without a bending magnet, the energy spectrum can be quite complicated. And it's very cumbersome to measure directly the energy spectrum. There are approaches like magnetic spectrometry that can be used, but as far as they're pretty complex, and as far as I know, it's never been used for a flash beam. So if we want to, so at the shim, we have a Mobitron. It's a compact linac capable of creating flash beams. It's the one that is pictured here. And so if we want to have a good idea of our spectrum, we need to come up with a solution to resolve this. The general approach to resolve an energy spectrum from measurement is an approach called inverse spectrum reconstruction. So if you have a good Monte Carlo model of the linac head, then you can simulate for each monoenergetic energy that you can consider the dose distribution, and then you find the spectrum that best fits the measurement. However, this is a heavily ill-posed problem. There are tons of solutions that should more or less match the measurements that you've done. So yes, that's the general idea of inverse spectrum reconstruction. It's a heavily ill-posed problem. Like I said, for some conditions, especially when you have a bending magnet, you could approximate the distribution as a Gaussian function. So that's one way to regularize this ill-posed problem. So then you only have two parameters to fit, the mean and standard deviation of your energy distribution. When you cannot really assume a Gaussian function, there are approaches that have been proposed in the past. One of them is to use a optimization approach called simulated annealing, where we changes the weights of each energy bin slowly to find something that converges towards a solution that minimizes the cost function. So a solution that really reproduces the measurements accurately. One issue with this approach is that it doesn't guarantee that you're going to achieve a physically realistic spectrum. You're going to get a spectrum that fits the measurements that you've done to optimize the spectrum, but doesn't mean that's a spectrum that is physically plausible. And there's a high risk of overfitting to your measurement. So if you change your SSD, you change your field size, you change anything in your beam, you might not, the spectrum you've optimized might not reproduce those measurements as well. So our objective was to find something kind of in between the Gaussian regularization, where you're heavily constrained but not physical, and then the simulated annealing, where you have a lot of degrees of freedom but still not physically realistic. So we took a step back and we tried to look at where does this spectrum come from, and it comes from the acceleration of the electrons in the waveguide. And actually, if you talk to the vendor, it's also information that you can obtain, the specs of your waveguide. And if you look at what the electric field looks into a waveguide, for a standing waveguide, it can be described as this function here. And there are some parameters in this equation that can be obtained by the vendor. So and you can also obtain the size of the cavities in the waveguide. So if you look at this, there are basically only two unknowns and that's a specific case for the Mobitron. The Mobitron is made of two consecutive waveguides, so they both have their operating field amplitude. So there are only two unknowns in the acceleration of the waveguide. So if you know all the vendor provided information, you could resolve the acceleration of the electrons in the waveguide using only two parameters: the electric field amplitude in the first and second section of the waveguide. So we implemented a Runge-Kutta algorithm to solve the electron beam dynamics as a function of the electric field in the waveguide. So then for any possible couple of electric field amplitudes, you can get a spectrum at the end. However, we could not solve for a static couple of electric amplitude in electric field amplitude in the two waveguide sections, as the amplitude of the electric field changes during a single irradiation, even during a single pulse, due to variation of the RF power, beam loading, gun current fluctuation. But yet, what we could do is to constrain the solution to just a few realistic couples of electric field amplitudes in the waveguide. So that's what we've done here. So we've modeled the waveguide, the acceleration of the electrons for a large combination of electric fields amplitude, and for each combination, we get a spectrum at the end. And then the final spectrum is just a weighted sum of these physically plausible spectrum. So instead of fitting the energy weights loosely, we solve the electric field amplitude in the waveguide. So that just ensures that at the end, we get a physically realistic energy spectrum. It's a spectrum that can be obtained given the specs of our waveguide. So we've implemented this method, and we've compared it to the two methods I've discussed earlier, the simulated annealing and the Gaussian regression. So the simulated annealing is in kind of bluish, the Gaussian regression is in purple, and what we obtained with our proposed model is in black. So these are just the spectrums. So the spectrum that we obtain is in black. So one thing we can see here is that for the 9 MeV beam, so these are two flash beams. For the 9 MeV beam, all three methods kind of agree. And it seems that for in this case, the Gaussian regression can give a solution that is quite similar to the two other ones. While for the 6 MeV beam, we have really a kind of a disagreement between the Gaussian regression and the two other, mainly because there seem to be two peaks of importance. One more thing to observe is that the simulated annealing will have this low energy tail of electrons, and these kind of emerge because they don't really affect the measurements. They're probably stuck in air or scattered, so you don't really have any information to solve this region of the spectrum. But it's not because they don't matter in your commissioning measurements that they will never matter. So that's an example of where constraining to a physically plausible spectrum might give you some edges. Now, in terms of reconstructing the isodoses, so here we're showing for the 6 MeV beam, the measured isodose versus the reconstructed ones and the error on the side, using the Gaussian regression and our approach. And you can see that the root mean square error is significantly reduced using the proposed approach. So that work was led by Samuel Audet, a master's student in my group. So the conclusion of that work was that we developed a novel physics-based approach that can derive the full energy spectrum from a compact linear accelerator without a bending magnet, using only a limited number of free parameters. We constrained the solution to only physically plausible spectra using only 2 parameters. And the method was shown to yield superior accuracy than reference approaches for flash electron beams. And one more asset of this method that I haven't showed here is that we could potentially do a full modeling of some very complex effects happening during the irradiation. So that's one thing we've observed. Our energy spectrum changes with the pulse width, for instance, and that's just because the beam loading changes when you have longer pulses. So with our approach, we could potentially be able to model that and predict how the energy will change for different irradiation parameters. We haven't done that yet, but that's another potential benefit of the method. Now I'll discuss some work we've done on another issue, which is the ability to monitor the beam in real time. So for electron beam, flash beams, beam monitoring is challenging. The ion chambers that are typically used, the monitor chambers, are saturating in the flash regiment. So it's challenging, but for electrons, there's a solution that has been proposed and actually implemented in a lot of compact flash linacs, which are called beam current transformers, or BCTs, that can monitor the beam in real time. So they seem very promising, but there are several studies that have shown that they are very sensitive to the radiation setup. So if you change your SSD, if you change your field size, the signal measured by the BCT is going to change drastically. For instance, there's a paper that reported differences up to 12% for short versus very long SSDs. And the mechanisms to explain this behavior so far was the following. So that's the way a BCT works. You have a ferromagnetic toroid, and when you have a charged particle beam going inside the toroid, it's going to induce a magnetic flux. This flux can be detected by a conductive wire wrapped around the toroid, and then you get a current that you can directly link to the beam current. So that's just the Maxwell equation explaining how all of this works. Then if you have a surface really close to your BCT, you might have backscatter. You might have electrons that go backwards. And these electrons going backwards in the toroid would induce a current that oppose the one of the primary beam, and then you would get a different reading. So that was the theory so far to explain these changes in beam current transformer signal as a function of the irradiation setup. It was mostly led by electron backscatter. So like I said, we have a flash-capable Mobitron at the shim, and we have an externally mounted beam current transformer, as shown here. So the first thing we wanted to do was to try to reproduce what was achieved by other groups, showing this large changes in signal as a function of the SSD. So that's what we are showing here. That's the BCT signal as a function of the SSD for the 9 MeV beam in red and the 6 MeV beam in blue. And what we're seeing here is that we have a sharp decrease in the signal when we're at very short SSD by almost 20% compared to what we have at very long SSD. So that was just reproducing what was observed before. That's true for the SSD. It's also true for the field size. So in this case, we place our BCT in a 3D printed applicator in which we can put collimators to change the field size. And depending on the size of this collimator, we get a different reading. So when we have a smaller field size, we have a lower BCT signal, which would work with the backscatter hypothesis. You have a larger area of the collimator exposed to the beam, so potentially more backscatter. So here again, about 15% signal difference for a smaller versus larger field size. So that was we've observed that was in working with what was in the literature. So we wanted to understand what was happening with all this backscatter. So we wanted to model this backscatter using, we had this nice Monte Carlo model now. So we wanted to model it and see if there's anything we can do to reduce the amount of backscatter going in the BCT, because it was kind of annoying. But the results we obtained were kind of not working with the experiment. So here I'm showing the fraction of backscattered electrons on a water phantom as a function of their energy. And what we see here is that for anything above 4 MeV, there's less than 1% of the electrons that are backscattered. So that means that even...
Sorry, are you in the talking one?
I did just join it, but
I think
that's
we're
okay.
It's working. Can you mute, please?
I'm so sorry.
No worries. Yeah, so what we're seeing here is that the fraction of backscattered electrons for anything above 4 MeV is much lower than 1%. And to remind you, like our energy beams are 6 and 9 MeV, the effective energy at least. So even if we had all the backscattered electrons detected by our BCT at short SSD and non-detected at very long SSD, we shouldn't have more than like 1% difference in BCT signal. But that's not at all what we're seeing. We're seeing up to 20% signal difference. And even if we consider very low energy electrons, it's never more than 5-6% of the incident electrons that are backscattered. This is true for water. It's also true for other materials. We've simulated water. Here I'm showing for two energies, 9 MeV, the triangles in red, 750 keV, the circles in blue. So for water, PMMA, acetal, that's the plastic from which the collimators are made. It's all much less than 5% of the incident electrons that are backscattered. Actually, to get something close to the 20% we're observing experimentally, you need to irradiate lead, and that's not what we're doing. We had that just for solid water phantoms. So this was kind of confusing, and actually we did a lot of back and forth, tried different settings in our Monte Carlo simulations. We would never get something close to what we see experimentally. So we took a step back and thought, we're simulating water. What happens if we irradiate water? And the result was actually quite surprising. So here I'm showing, that's the pulse captured by the BCT as a function of the SSD for water in blue and solid water in orange-ish red. So for water, actually, we get something that agrees very well with the simulation, what the simulation predicted. We basically get the same pulse shape, same signal, no matter what the SSD is. But for solid water, which is what we irradiated to observe the effect earlier, the signal is very different at short SSD. And then as we get further away from the BCT, the signal gets closer to the one of water. So at short SSD, we have a ratio of the area under the curve for solid water to water of about 15%. One thing you can observe is so that's really surprising, because water and solid water are assumed equivalent. We've always assumed that solid water is like water. It's been optimized to have the same interaction properties as water. So there's something odd happening here. And one more thing you can see is that it gets worse as the pulse goes. So for longer pulses, the impact would be even bigger. It's true within the pulse. It's also true for one pulse to another. So here we're showing for an irradiation of 5 pulses in a row. For solid water, we have a decrease after the first 2 pulses, and then it kind of stabilizes after the third one. While for water, the signal is rather stable. And actually, this effect, this decrease in signal, we've seen it for a while, and we thought it was the machine, the output of the machine decreasing after as it was giving pulses. But when we irradiate water, we don't see that. So it's really an artifact of the BCT. It's not something physical from the machine. So this was quite confusing. Now what we see is that the effect gets worse within a pulse, and it gets worse from pulse to pulse. So it seems like there's something building up. There's an artifact that builds up. And considering that the main difference between water and solid water is their electrical conductivity, we made the assumption that maybe there's something related with the way charges builds up in solid water versus water. So to test that, we tried to ground our solid water. So we took our 5 cm solid water slab. That's more than the range of our electrons. So the electrons don't go beyond that solid water slab. And we placed an aluminum foil just under it. And whether we grounded or not that foil, we had a different pulse shape. So when we ground the aluminum foil, so we let the charges that accumulate in solid water dissipate faster, we get a pulse shape that looks like the one of water. When the aluminum is there but not grounded, then the charge just builds up in the solid water. We see this artifact, this decrease in pulse shape measured by the BCT. So now it really kind of indicates it's related to the way charges builds up in solid water under flash conditions. Now, how does that affect the BCT? It's still not clear. So we made the hypothesis that you have this charge that builds up in the solid water. This must induce an electric field. So if we shield our BCT from the electric field, we should resolve this. So that's one thing we tried, and we actually have a provisional patent on this. So we took our aluminum foil and we just placed it downstream of the BCT. And when you ground this foil, you put it to a constant potential, it acts as an electric field, an electrostatic shield. So no electric field line can go through the BCT. When the foil is there but not grounded, it's transparent to the electric field. It's gonna go through the BCT. So we did this experiment of comparing the signal when we have the electrostatic the electrostatic shield either grounded or not. So the aluminum foil is there no matter what. It's just the fact of grounding it to activate our shield. And when we have the shield in place, then we perfectly resolve this SSD dependence. We see the same pulse shape from 25 to 50 cm SSD. When the aluminum is there but not grounded, then we still see this effect of pulse shape that changes with the function as a function of the SSD. So it solved the SSD dependence. It's also solved the water to solid water difference. So now we have a perfect agreement for the signal we measure when we irradiate water versus solid water, as one should expect. And it also resolved the field size dependence that I showed earlier. So this really clearly indicated that what we were seeing was an artifact induced by the charge buildup occurring in plastic. So not only the solid water, just the collimators were also creating this artifact. And we could prevent the electric field line to reach the BCT to solve the issue. Now, does it make sense that the BCT is affected by the electric field? That's another question. We think it does. So I go back to the mechanism I've shown earlier. So you have your primary beam going in the toroid that induces a magnetic flux in the toroid that is detected. Then if you look at the full Maxwell equation, there's also a term for a varying electric field in time. So if this electric field builds up, and it should as you radiate, there's a term that accounts for this variation of electric field with time. And the direction of this induced magnetic flux opposes the one of the primary beam. So that's one way the charge buildup could affect the BCT through an electric field. We think there's actually a second mechanism that is probably the main effect. So as you all know, when you have a ionizing beam in air, it produces charges, right? It produces electrons and ion pairs. And when you have an electric field, those pairs might not be combined as much. So we think this is actually the main driver of the effect, is because the electric field can reach quite substantial values. We've made back of the envelope calculations showing that it's probably a few tens of kV per meter that the electric field can reach within a pulse, which is similar to what we have in the Farmer chamber when we apply a 150 bias. And we know that with this bias, we collect quite a lot of charges. So we think this is actually the main driver. Is you have your primary beam, it creates pairs of electron and ions. When you don't have the electric field, they recombine. When you have an electric field, they start drifting and induce a current opposing one of the primary beam. So the conclusion of that work was that we've shown that the electron backscatter for MEV beams on most material is way too low to account to explain the significant beam current transformer signal variation that were observed by other groups and reproduced by us. We've shown that the BCT's signal is in fact strongly affected by an electric field induced by the transient charge buildup occurring in solid water and any actually non-conductive, not perfectly conductive material irradiated by ultra-high dose rate electron beams. Introducing a electrostatic shield downstream of the BCT successfully removed all the SSD field size and phantom material dependence of the BCT signal, and all the details were published in a paper in PMB earlier this year. So once we had this nice tool once we corrected this very promising tool to monitor the beam, we wanted to know how accurate it could be. Once you get rid of this artifact, how accurately can it actually track the dose? So that's some work we've done in collaborations with colleagues from the NRC in Ottawa. And they provided us with alanine pellets, which are referenced, they're dosimeters that can be traced to primary standards of absolute dose to water. And they're really the reference for flash regimen. They're dose rate independent. So you can get a clinical accuracy of dose below 1% with alanine. So they shipped us the alanine by mail, and we calibrated our BCT. So we created a dose to charge relationship, the charge measured by the BCT versus the dose absorbed to a point downstream of the BCT, the same way we do for monitor chambers in a standard linac. And we wanted to see how stable was that relationship, and could we rely on it to report the dose delivered in flash conditions. So we've done this calibration. Here I'm showing the calibration conditions. So we were at 6 millimeter depth in solid water. We aimed for a dose of about 25 gray because alanine is reliable for 20 grays and above. And we had the same conditions for both our 6 and 9 MeV beams. Once we've calibrated it, so the calibration was done by doing 3 sequential acquisition for both energies, and then we took the average and got our calibration coefficient for each energy. Once we got that, we assessed the stability of this calibration over short and long-term periods. So we did the first 7 days, and then we did weekly measurements for the following 16 weeks. And we also looked how stable was that calibration against variation in the irradiation parameters. So here are the results we obtained. So that's for the short term, the first 7 days following the calibration. So we're showing the above is for the 6 MeV beam, in the middle is for the 9 MeV beam, the dose reported by the alanine, measured by the alanine in blue, and the one predicted by the calibrated BCT in orange. And below we have the difference between the two. And we see root mean square errors below 0.2% for both energies for the short-term period. For the longer term, we also have a very good agreement. Actually, it always stays within 1% over 4 months. So we had very good agreement between the calibrated shielded BCT and those measured by the alanine. And a few things are worth mentioned. So first, during the week 11 or just after week 10, we had a maintenance. So the interrupt came and made some changes to the machine, and that resulted in a change of output by almost 10%. So following the maintenance, we made sure that the energy was the same as it was before, but the output had to be adjusted a little bit. And despite this output change, we still tracked. So we didn't recalibrate the BCT. We just kept going with the same calibration, and we were still within 1% after the maintenance. The other thing that is worth mentioning is for 1 day, we actually were lucky. The Mobitron is very stable, but every now and then it can happen that there's a pulse that is not emitted properly, and then this happened on week 11. So we see here that the third pulse actually had an odd shape. It wasn't just like partially emitted. And what's interesting is that if you take the integral of this signal and you account for it, and then you compare it to the dose measured by the alanine for this irradiation, we're still within 1%. So that's actually very reassuring, because if the machine can have issues, but as long as you track them properly, it's a good sign. So that was also a very positive result. So we've shown that it's extremely stable, very accurate, within 1% for months without recalibration. So very reliable. That's for as long as you don't change the setup. Now we've tried varying some parameters, and that's something that is relevant. Like, because if you're doing preclinical experiments, you want to create dose response curves for quite a large range. If you're translating that in the clinic, you might need to adjust the dose depending on the prescription. So we wanted this calibration to stay robust to moderate changes in the pulse parameters. So by changing the pulse width, for the 6 MeV beam, we've stayed very close actually to the reference condition. For the 9 MeV beam, we see a little drop in the accuracy, so the agreement between the BCT and the alanine. And this directly comes from what I've talked about earlier. The energy changes with pulse width. So depending where your calibration point is on your PDD, if you're in a region of higher gradient, you might just be more sensitive to that. So we don't think it's the BCT reporting the wrong dose. We just think it's the dose changing, basically. We were very stable, again, within 1% with the number of pulses, and stable also with pulse rate frequency, which also can affect the beam energy. So we think all these discrepancy come from changes in energy. So one way to account for this in the clinic, even though the changes are not very large, one way to account for this would be to just check the energy prior to irradiate, which is something that the beam current transformer cannot do. It just reports the current. It doesn't report the energy. So it needs to be matched with another detector that could do some energy check prior to irradiate. So here we're showing the linearity with dose. So I'm combining when we vary the pulse width and the number of pulses. These are two ways to change the dose we deliver with the BCT, and we have a very good linearity, which is again quite reassuring. So the conclusion of that work was that we were able to successfully implement a calibration procedure to monitor the dose with our BCT in the UHDR conditions. The shielded BCT implementation was able to track the absorbed dose within 1% over 4 months, despite significant output variation. To put that into perspective, previous studies that tried to do this with an unshielded BCT had stability more in the order of 2, 3, 4%. So it's a substantial reduction. The calibration was shown to hold for a wide range of pulse width, number of pulses, and pulse rate frequency. And considering all this, we conclude that the shielded BCT is a quite reliable and promising solution to monitor the dose we deliver with our flash beam. So just to give you that kind of wraps the work we've done in our group. Now I just want to mention a little bit what we plan, what's coming. So we're in the process of optimizing our applicator now that we know that the shield is really necessary. Otherwise, you cannot use the BCT measure in a reliable manner. We're re-optimizing all our, we call it our ultra high dose rate expansion kit, because it's important to know that our Mobitron is also used clinically in the conventional mode. So everything we add for flash needs to be kind of self-contained and added to the machine. So we're fully re-optimizing this applicator. We're also, the idea is to piece everything together. So we have our good Monte Carlo model. We have this BCT that can track the absorbed dose quite accurately. Now, if we want to predict the dose in a mouse, a patient, or any other geometry, then the Monte Carlo is going to do the link between the two. So once we have all these pieces together, we're in the process of validating that with end-to-end tests as we do in the clinic. So we're developing a small animal phantom in which we can incorporate dosimeters to validate that the dose we predict with our Monte Carlo and that we monitor with our BCT, everything agrees. And one thing that is kind of maybe a pie in the sky, but something that could be investigated. So now that we shield the BCT is actually giving an absolute measure of current. It's the absolute current of the beam. So if we know that, it's also something we can simulate with Monte Carlo. So in theory, this conversion of charge to dose relationship, we might not need a dosimeter to measure it. If our energy spectrum is well characterized, we can directly predict that just based on a fluence measurement. We're not there yet. We're trying to assess how realistic that is, but having this absolute measurement of the fluence, which is not something we're used to in radiation oncology in general, might allow us to do absolute Monte Carlo simulation, which could be quite interesting. So yeah, I just want to thank my amazing students that worked on this and you for your attention. I'll be very happy to answer any questions.
Not a stop. Okay.
Let it run.
Are there any questions for Professor?
Yeah. This is great. Thank you. Lots of physics in your talk. This charge buildup in the solid water, is that like a known thing, or
It wasn't until you know we.
curious if you touch it, do you get a shock?
So I think if you deliver quite a lot of dose, you might. So it's not fully true. It was known like in the 80s, people used to do QA with PMMA. And it was shown that if you're doing electron beam QA with PMMA, so PMMA there's long-term charge storage in PMMA. That's how you create these electron tubes. I don't know if you've seen them. We're actually creating them with our flash beam. So PMMA really do long-term charge loading. And it was shown in the 80s that after a month or two, like your chamber response might start drifting because of the electric field induced by all this charge storage. So that's why solid water was optimized not to do long-term charge storage. But what we're showing is when you're beating when you're irradiating at a dose rate that beats the charge dissipation rate in the phantom, you might still see this effect.
Is the reason why you don't see it in solid liquid water because purely from dielectric?
Yeah, so the charges in water will dissipate faster, probably to the wall of the tank. So whether you have a bigger or small tank, you might see a different response. So that's actually a question we get often, was like, well, why don't you ground everything you irradiate? Well, it's not fully realistic, so that's one thing. Like if you irradiate a patient, how to ground them. And also we've seen for water, depending on the size of the tank, you might get a different reading because the charge will just go to the side, right? So it just depends where they go. But so the decision we've made is that there will be charge buildup. That's something we've shown that happens in flash conditions. Now it's just to isolate your detector from it.
Any other questions from the Zoom? I have maybe one question. Most of your research is done using the Mobitron, so a compact linac. For example, your physics-based approach to the Monte Carlo modeling, is that easily translatable to other types of linacs that can produce high dose rate?
So I think if you have a bending magnet, it would be complicated. And I think in those cases, probably just a quotient function would work well. But we do think it would be applicable to other flash linacs, not just the Mobitron. It would actually be easier for those that just have a single section. Mobitron is a special case where you have these two sections of the waveguide, making the modeling a little bit more challenging. But yeah, we think it's relevant for any linac without a bending magnet.
I was interested in that part too. Yeah. So waveguide physics, it's been a while since I took E&M. Those like quasi monoenergetic basis functions that you're getting, are those related to just like solving the Maxwell's equations in a waveguide?
Yeah, exactly. Yeah, which with the so and it accounts for like the response of the waveguide for the electron. So it's not you have an incident energy and then you get a monoenergetic spectrum at the end. It's really a spectrum that accounts for the phase also of the electrons within the waveguide. And
so is this something you have to solve analytically?
Yeah, and numerically.
Yeah, you can't solve it.
I mean, there are ways, but I think the assumption would just be too important to make it kind of reliable.
And I guess again, the bending, is that because you're now doing an energy select or because of the like a mass spectrometer? Because I would imagine the energy spectrum of the electrons coming out of the waveguide before you bend it.
Yeah, it's exactly the same. Yeah.
And then after bending, you're basically just pruning and getting the Very nice.
So to model the spectrum, you're using just vendor provided values
for the size of the cavities in the waveguide, the operating frequency, the incident energy of the electrons from the electron gun. But we've done like a sensitivity analysis, and like the energy of the electrons out of the gun can be, you know, plus minus 50%, doesn't change much. The spectrum in the end, it's really the size of the cavities and the electric field amplitude. But that's what we solve in the end.
And did you test it on other Mobitrons, or because
No.
basically your spectrum is one spectrum for all Mobitrons?
Well, so no, actually it changes. It's very, very sensitive. Like when we've done this output change, it's really pushed at like the maximum of this capacity. So when you change the pulse width, actually the spectrum changes, and the number of pulses too. So you gotta solve it for like a set of conditions, and we try to stay as close as possible to these conditions. But you know, I'm pretty convinced that for a different Mobitron, we would get a different spectrum in the end for the same nominal energy, because we've seen it for just our machine. When after maintenance, spectrum is changed, and then we have to redo the whole thing.
There's no more questions. We can thank Arthur Lalonde again for his time.